Welcome to Get in Gear Science Educational Standards. This is lesson 3. Maybe going to try to finally read a little bit between the lines about what all this information kind of means. And I want to start off here. I've mentioned a little bit there's next generation science standards, a little bit newer than the Common Core educational standards in the United States. Maybe just kind of talk briefly about, some of the strengths, some of the weaknesses there. There's always strengths and weaknesses. The one thing that I kind of want to talk about, my personal teaching philosophy is sort of related to what might be called context-based learning, and I'm not sure if this is really an emphasis in any educational standards that I know about. I want to talk a little bit about modeling and, for that matter, engineering, something that's included in the next generation science standards, a kind of new thing, and a little bit about, how courses might fit into various educational science standards. So as far as, the next generation science standards go, I think there's a lot of strengths there. Kind of the big idea, we talked about this in lesson 2. I kind of gave an example of a storyline, right? So they were kind of using this, I'd mentioned an example where we were kind of talking about water in your house. Where does it come from? Where does it go? Having a story that kind of builds up to understand, what water does in the environment, the weather, where sort of water come from and go, but starting, with a personal story. And I think this is really the way to go. Everybody prefers a story over, just a big list of facts. It just kind of makes more sense that way. It engages the learner. And I think I mentioned just a moment ago that the next generation science standards, one of the new things about it is it covers not just, traditional science, but starts to get a little bit into engineering, mathematical modeling. These maybe, used to be more type of college level type of things, and they're being introduced into the K to 12 curriculum. I think that's great. We'll maybe look a little specifically about what that means. And as far as another strength of the NGSS, I think it's really well documented, which is good. It is a lengthy document, and I sort of mentioned that it was broken down 2 different ways by both, core ideas as well as topics. And I know this, kind of makes the document lengthy, maybe can be a little confusing, but it's kind of nice they did it both ways, depending if you're a teacher trying to come up with lesson plans or evaluate, how effective the teaching was. I think it kind of makes sense to organize these in different ways. So I think that makes sense. And, these topics maybe connect a little bit better to storylines than just kind of a list of individual ideas. So at any rate, right, there's a lot of information there, but I think it's really well organized. I think they did a nice job of organizing it, and you have to understand, though, and I consider this a strength. You have to understand, right, that even though there's it's a lengthy document, but it's not a cookbook. You can't look at this thing and come up with lesson plans per se, right? It's something to kind of evaluate if what you're teaching is kind of a good way to be teaching science or not. So that makes it maybe not as easy to use. You can't just pick it up and find lesson plans out of it. And yet I think obviously they don't want to be over restrictive, telling teachers exactly what to be teaching at the lesson plan level, right? So it's not just do steps A, B, and C in order and you have taught science type of thing, right? Rather, it's a way to sort of evaluate if your science program is up to par. And, I think that's kind of a good way to have things. Now, as for the last strength too, there's a lot of momentum behind next generation science standards, you might say. There's a bit of a user community. I showed you some examples in the previous lesson of this Get in Gear course, some places to get lesson plans and such, people that are making materials that are aligned with the NGSS. And I think this is great. So, keep those lesson plans coming. They're obviously, a valuable resource, and people continue to kind of build on them and twist it around and make it their own. And, it's going to take a little time in the long run. That's going to possibly make for some really great science teachers, which is, kind of the necessary ingredient in the whole recipe. I don't want to gripe about NGSS. It has its weaknesses. Everything has its weaknesses. And, this first one you could probably say about sort of any sort of science curriculum type of thing is, it's still kind of written by science people for science people. And of course, most of the end users, you might say, the learners, the parents, they're not themselves scientists. So, there's just kind of some disconnect there. And then as far as the second one, now I love this idea of storylines, and yet it's not quite the same as context-based learning. I sort of want to maybe show you what that's all about in a couple future pictures. And then this number 3 here, I have a problem with, this concept of science being based on math, since about the time of Einstein. In fact, one of the things that, Einstein was trying to do was boil all of reality down to a single equation, right? There's a lot of scientists, mathematicians that have believed for a long time that math is like kind of behind the science, and you need to understand math to understand science. And I don't really think that's true. I think that math is a tool that scientists use, much like a carpenter might have a hammer and a saw as different tools that have different applications. And I think there's a lot more to be said about, the right type of math being applied to the right type of problem. And I kind of wish the world would maybe move away from this, science based on math stuff. They say that science or math is, kind of the common language of science, which is true, but, it's maybe kind of like saying, well, somebody that speaks Spanish can't understand a concept that's explained in English. And I think there's lots of ways to conceptualize, to think of things without trying to make everything math. I don't think, as a scientist, I don't think math is really behind everything. I don't think it's a good way to be teaching things, especially to youngsters that understand, concepts better than math in the first place. And now I'll talk a little bit about this, when my interpretation of what an engineering course should be, to me, has a little bit of, using the computer to analyze things. And, there's lots of engineering that doesn't. There's all sorts of hands-on activities, laboratory experiments, and such. My personal direction, I think K through 12 learners need more computer skills. So that, to me, falls under the category of engineering, maybe not as emphasized in any of these, science educational standards. And then, another big thing too, I kind of, talked about, especially chemistry, physics, these old fields, right? They're kind of this top-down thing from university professors, what a university science class should look like, what high school students should be taught to get in to university, and it's kind of that all top-down approach, like building towards what, people should know by the time they are in a college science program. Not that everybody's headed that way, but that's the way these, K through 12 science programs are built. And as such, right, it sort of started from the top, and they've tried to break it down into simpler and simpler concepts. And yet, there's this big fear of teachers about having a watered down class, whatever that means. And, I feel that it's, kind of broken into parts in a way that's sort of overly precise. It's geared towards not being wrong, having lots of superly precisely defined jargon, and it's sort of the opposite of being watered down. It's a lot of information, but it's not necessarily related to the learner at the stage of the game they're at in third grade, maybe not yet thinking about a college sciences program. And then speaking of that, who is the audience here for next generation science standards? Are we teaching people that are going to college to get a science degree? Or are we teaching, quote, lay people that, might be people that don't go to college, people that go to college but want an arts degree, right? Who's the audience here? And I just kind of point that out because, the next generation science standards has this concept of advanced materials. And if you really kind of want to be, college prep oriented, you need to go above and beyond the next generation science standards, do this advanced stuff. And yet, is this basic stuff maybe a little too much for, everybody? Maybe there was kind of two audiences there, and it ended up as one standard at the end. So I'm not quite clear if we're talking about science for everybody or kind of more college prep science, which, is sort of the way that things have been for many decades in a lot of the Western world. And then one other thing that's kind of interesting about the engineering, it mentions some laboratory stuff in the next generation science standards. And, science teachers kind of have this concept of so many, counting hours spent in the laboratory, counting experiments successfully performed. And I don't really think this is a good way to count. I'd rather have one good experiment where people learn something that's really simple versus 10 complicated experiments. But there's this, I guess, tradition, belief on the part of teachers more so of counting hours, counting experiments, checking off the progress, and this is maybe a little bit different. The next generation science standards, which is more focused on what the learner learns, which is good. But yet, I guess what I'm saying is, how do we break the science teacher's habit of counting hours, counting laboratories? This is kind of often how curriculums and lesson plans are built. So let's move on here. I want to talk a little bit, about storylines versus context-based learning. And, they're both a giant step forward from the old school of sort of memorize, this Isaac Newton statement from some 100 years ago that used to be kind of how it was done, right? And then we talked a little bit about, developing this into storylines, and this is sort of what the next generation standards is all about. You might call this sort of new school, not memorizing facts, right? But an idea, a concept, a story, something that sort of starts at home. Where does the water come from out of the spigot? Where does it go down the sink? And how is that all connected? Where does water come from? And where does water go? So, I think that's a good way to do it. It's a story that people can relate to, right? And yet, it's still like a little bit, in a sense, you might say, sort of top down, right? It's sort of based on, telling a story to get to the point of what learners should know at a certain grade level, right? And what we call context-based learning is a little bit different. You might say it's a bottom-up approach, in the sense that it starts with things that you already know, basically by analogy, relating things that you already know to new science concepts, all right? It's maybe a little bit more creative and, of course, a little bit more open-ended in terms of developing lesson plans, and yet, there's been a lot of studies out there that sort of shows that this is what connects with learners. It, gets them motivated for science, which is kind of the most important thing. So we'll look at a couple examples here to kind of maybe show the difference of what I mean by context-based learning. And again, this is maybe kind of a new thing as far as education is concerned. I mean, it's an old thing. It's been around forever, but it's, becoming kind of popular among, some educational professionals in recent years. So maybe something we can kind of hope to see in the next generation of educational standards for science teaching, because of course there will be something new coming out at some point. And the main difference here, right, the storylines I think are cool. It's a great idea. It makes logical sense to connect all these logical ideas. The main thing about the storylines is that you're taking logic that they already know and kind of building up the pyramid of logic, right? So there's kind of this philosophy that if it's not logical, it's not science, and it has no place in the science classroom, right? But only part of your brain is logical. You might say you've got an analogical part of your brain, of your mind, the part that thinks not in facts and steps, but the analogical part thinks by analogy, right? So there's all sorts of stuff you already know that's a perfect analogy to science, right? So why can't we use that as a basis of teaching instead of trying to build up this logical pyramid in a way that doesn't fall over? So we're going to talk about two examples. And I specifically here, we're going to talk about, I specifically picked the two biggest words out of a chemistry textbook that I could find just to sort of prove my point. We're going to talk about electronegativity and stoichiometry, right? Maybe some scary looking words if you've never seen them before, right? And we'll kind of talk about, how this can be made really easy in a context-based learning approach, right? So electronegativity, this is the way that I teach it. It's pretty straightforward. It's electron piracy, right? So this is the context-based learning approach, right? Do you understand the concept of a pirate, right? So if you can understand the concept of a pirate taking something, right, you can understand the concept of electronegativity. Now, we're not literally talking about pirates, of course. This would be in a chemistry class. The pirate represents an atom, right? And this atom is going around basically stealing electrons from other atoms, just like a pirate would be pirating things from other people, right? So that's one way. That's the context-based learning approach, right, as opposed to the sort of logical approach, right? So you can look up electronegativity in the dictionary and you get a measure of how strongly an atom tracks bonding electrons to itself, and the ability to gain electrons, gaining electrons, I guess, is a little similar to the piracy here. And then definition 3 came out of a dictionary. I guess it's a technically correct definition, but it really has nothing to do with a chemistry class, right? And that's kind of the problem with logic. Just because something is true doesn't make it relevant to the task at hand, right? So you might ask what an electron is in case you didn't quite follow the electron piracy thing. Well, you could take the logical approach. You could look up an electron in the dictionary and it's an elementary particle. It's a fundamental constituent of matter having a negative charge of some coulombs, a mass of some kilograms. atoms, a spin, and it goes on and on and on and on. All these little facts that you need to know to kind of build up the logic pyramid to understand what an electron is, right? But maybe back to the context-based learning approach, right? Electronegativity is electron piracy, right? Like atoms stealing electrons. And the analogy here is that these electrons are kind of like the currency of the atomic world, right? A lot of times when people do something, there's a transaction with money involved. Electrons, I don't believe atoms have paper money, but rather they have electrons, right? And when something happens, these electrons are traded, and every now and then we have some not so fair players that are more into stealing than trading and sharing fairly, and that's kind of how the economy of atomic structure, you might say, works. So that's kind of one example of the context-based learning. Again, just electron piracy, right? Piracy is a concept that, most people can understand regardless of the language they speak, and you might notice there that the picture is maybe kind of worth almost 1,000 words. So that's kind of one of the nice approaches of context-based learning, as opposed to the logical learning. If you wanted to understand electronegativity the logical way, you need to know the definitions of elementary particle and matter and charge and Coulomb and everything on this list. And if you looked up those words, they'd have other vocabulary words in it, right? And that's sort of been this approach, with a storyline or not. It's logic stacked on top of logic, stacked on top of logic, and, it does get there. And yet, is it the best approach to connect with a K-12 learner? I'm kind of thinking not, and the more I think about this, I sort of wonder if there really is even a basis to this logic period, or if it's this logic pyramid, or if all logic is a little bit circular in the first place, and it's kind of all interdependent anyhow. So anyhow, we have sort of the logical approach to learning science versus the more context-based. You might call it analogical, right? I just say it's learning by analogy, right? You get the concept of a pirate taking something, right? Maybe you can understand the concept of an atom being a little aggressive and ending up with more electrons, more currency than its neighbor. So anyhow, all this logic was starting to make me hungry a little bit, so I got out my second example of a context-based learning approach, and this is what I do in some actual kind of more advanced chemistry courses that I teach. We get to this topic called stoichiometry, the second giant word that I introduced you to. And again, you could look it up on the internet. It's the branch of chemistry dealing with relationships and combining elements, especially quantitatively, whatever that means. So what we're talking about here, right, is, cooking is chemistry, right? We mix a bunch of chemicals together, we stir it up, we get some sort of a product, right? So say this might not be the best muffin, but imagine you could make muffins with 2 eggs and a cup of flour, right? All that this giant concept of stoichiometry is saying is, hey, the ratio is 2-to-1, right? So what's going to happen if you have a couple eggs and a dump truck full of flour? Are you going to be able to make more than 2 muffins, right? Or are you kind of limited by the ratio that you're given in the recipe, right? So this is, I don't know, several chapters in a chemistry textbook, usually where learners lose interest in chemistry when this concept of stoichiometry comes up, and yet, all we're talking about is a recipe with a 2-to-1 ratio, right? I think a lot of people can connect to the concept of a recipe, as soon as you change the word to stoichiometry and you start talking about chemicals instead of eggs and flowers and things people have actually put their hands on, right? Most of the point is lost, no matter how logical and true it happens to be. You want to, find a way to connect to the learner by analogy, right? Based on the context of something simple they already know, like a 2-to-1 ratio in a recipe. So at any rate, that's sort of my spiel about context-based learning. I think it's the way to go. I hope we see more of that in the future. The other thing I was saying about the next generation science standards too, just, totally switching gears here about the engineering, right? Engineering used to be a thing you did in college. Now it's being suggested at the kindergarten level. So you might say that there is a bit of a paradigm shift there. Now, what exactly are we expecting a kindergartner or a K-2 learner? It's broken down by band. What exactly should we expect of a K-2 learner in terms of being able to engineer something? And now this, for what it's worth, is Appendix F in the next generation science standards. There's many more tables about, you may remember there's the engineering practices, the list of, science and engineering practices that, people should be doing, like asking questions, interpreting data, communicating. We talked about them, I think, at the very end of lesson 2. And sorry, I didn't show the list here because my intention is to paraphrase dramatically. And I'll remind you again, I have no affiliation with the next generation science standards. This is totally my, boiling, many pages of tables down to just a few lines of text. So it's obviously an oversimplification. Forgive me if this isn't exactly correct. And yet I think this is kind of more or less in the spirit of what they're thinking, at the sort of K-2 level. They should have this idea of like evidence, right? That they can, measure and observe things, somehow collect evidence, So that's maybe kind of at the K-2 level. It's a little bit more about evidence. Now at the 3 to 5 grade level, it goes a little bit beyond evidence to what we might call data, and they even sort of specifically suggest arranging data into data tables. I think this is awesome, data tables. I think this is maybe aside from computer skills, the number one engineering skill people need to learn is arranging data into data tables. Now, I'll be honest, I have a lot of university students that can't organize data into data tables. A lot of high school students can't do it. I often try to, sort of bring this in more so at the middle school level myself than the 3 to 5. So it's a good idea. And yet, where exactly, do we start kind of learning how to organize data into data tables? And then I guess the idea of kind of organizing data into data tables is, at K-2 level, they're just kind of observing things, they can measure it, there's evidence, now 3 to 5 level, is there enough data to really formulate a science question versus a non-science question? So kind of distinguishing between, what's provable and not provable based on observing the world. The K-2 level is more just this ability to observe the world, period. At the middle school level, it starts to get into kind of designing an experiment that would collect these data that would go into a table, testing hypotheses, maybe using some simple math and logic. And then at the 9 to 12 level, it's kind of scientifically about the math and modeling, being a little more rigorous with the math and modeling analysis. Oops, I'm sorry. It looks like my autocorrect butchered math and modeling analysis, excuse me, and you know, just practical things like real world limitations. I mean, can we do this in a high school laboratory, or do we need $1 million piece of equipment that's only in a national lab? And, you know, considering things like social justice and environmental impacts and the economics of different technologies, and just sort of kind of practical stuff. So that makes sense to me. I would say, though, it's, you know, it's all a little vague. It is all a little new, so I understand why it's all a little vague. Now, this is the one thing that I find really interesting here, right? I think we'll all admit that this engineering thing is new. It needs a lot of work. I think it's a good start, right? And here's the thing I found interesting. Not all of them, but a lot of the engineering practices are meant to build, right? That kind of makes sense. So what it says, you know, the stuff that we learned at the high school level is supposed to build on the middle school level. Good. High stuff at the middle school level is supposed to build on the 3 to 5 grade level. 3 to 5 level supposed to build on the K to 2 level, and that all seems to make sense to me. But if you kind of trace the chain back, it says that the stuff they're learning at the K to 2 level should be based on their prior knowledge. Now, what exactly do people know before they go to kindergarten? Now, I might argue that they know a lot, right? If you're using a context-based learning approach, they'd probably understand the concept of a recipe and a pirate, and we could explain, you know, some rather advanced chemistry concepts to a kindergartner if we really had to, you know, talking about a recipe and a pirate, right? But that's not what they're talking about. They're talking about the stuff that we know logically in high school should be based on the stuff we know logically in middle school, should be based on what we know logically in 3 to 5, based on what we know logically K to 2, which is based on what you know logically headed into kindergarten. And that is where I think the whole thing breaks down, because, you know a lot going into kindergarten, but it's, you know, it's context about the world. You haven't yet developed your logical mind, and to me, this is kind of where this pyramid of logic is not quite on a solid foundation. But nonetheless, right, I think this is a good idea. Maybe just to add a little bit of context-based learning along the way would kind of actually make this all work in practice. And again, it's not so much about changing the lessons with context-based learning, just coming up with a good analogy to start the class, to get their brain in gear, you know, relating it to something that they already know, not starting off with something foreign and abstract and uncomfortable that makes for a not fun hour of class. So the other thing that I like about next generation science standards, changing gears again, right? We got the storylines, we've got the engineering that I just talked about, and then there's also this concept of modeling, mathematical modeling. Now, I sort of had my little rant about science is not math at the very beginning of this course, and that's sort of, to me, been a misconception in the field for 100 years. A lot of people would disagree with me. You know, I think math is more a part of science than science is based on math. And, you know, I've put the modeling, for example, in my math courses. Like, for example, my Algebra 2 course, we see a fish here jumping from one bowl to the other. You might be able to see there's a mathematical curve. It's called a parabola. It represents fish flight paths and pretty much the flight path of anything here on planet Earth. So anyhow, my approach was kind of to put the modeling in the math, make the math a little bit more real, as opposed to try to put the math in the science and make it all about modeling. So those are just, you know, philosophical differences, I suppose. I do think modeling is a really important thing. I just think it makes more sense to kind of stuff the science in a math course and call it modeling versus stuffing the math in a science course. It's just too much to learn at once. you're expected to know the math before you walk into a science course. It rarely happens. And then you have to learn the science and the math at the same time in a science course. And it's, you know, it's just too much. We want to focus on one thing at a time. So kind of the last thing I was saying here, you know, the NGS, it's a checklist. It's not a cookbook. And, you know, you can't use it to sort of build courses. I just maybe sort of showed you what I've done with some of my courses here. You know, I made my courses the way I wanted to make them because I have a pretty good idea how to teach science in a way that connects with K to 12 learners. And then, you know, after the fact, I went back to the NGSS and looked at the different science topics and the grade bands and, you know, sort of checked where everything falls into place. And, you know, some of my classes cover a few different topics. Some focus on one. It just depends, right? But just making the point here, right? You can't use, you know, any of these. You can't use the next generation science standards sort of bottom up to build your curriculum. It's more of kind of a top-down check for completeness. So at any rate, that's maybe just one thing to say. It's nice for organizing and understanding, you know, an existing curriculum. You know, at the same time, though, it's not a cookbook. It's not going to produce a science curriculum for you. Now, one final point that I kind of want to make here, and this kind of falls under the category of context-based learning. Now, this is a course I have at the 3 to 5 level. It's kind of 8 history lessons about science, right? And the idea here is it's not like a factual history class. Like we kind of focus on like really general things like alchemists 2,000 years ago. Were they doing chemistry or not? Or, you know, like the concept of waves or animals that have parts that glow, or, you know, DNA, just kind of really general topics. And yet what we kind of looked at was not so much the history timeline, but we looked at what you might call the human element of the science and the engineering, right? So what were people thinking? Like why, what were people doing before this invention came around? What fundamental problem did it solve when people had this invention? You know, how did the course of world history change? And so on, right? So it's not just about what happened, you know, it's not just about the technology, the science, right? But how does this kind of fit into what we call human civilization and you know, just what were people thinking way back then when this was happening? And again, I just kind of find that it draws the learner into the story, right? And provides some context. So this, you know, for example, here was a story about the original manufacturing of dynamite, kind of a maybe interesting story. And if you see here the ability to mass produce dynamite by Alfred Nobel, you may have heard of Alfred Nobel before. He didn't invent dynamite. He figured out how to mass produce it. It didn't really have anything to do with chemistry, but rather you see here the last ingredient on the list is underneath this factory worker. It's a one-legged stool. You know, they had to cook the dynamite for 8 to 12 hours, and more often than not, the worker would fall asleep, and that would not be a good thing, falling asleep workers in the dynamite factory. So, you know, I guess it's a rude awakening when you fall asleep on a one-legged stool, but nonetheless, that was the key invention that made the manufacture of dynamite safe. It had nothing to do with the chemistry. It was focusing on the human element. What can we do to have this person sit there for 8 hours at an admittedly boring job, but without falling asleep and creating a dangerous situation for everybody? So just kind of a few examples there of, you know, where I think NGSS could be improved as far as, you know, kind of context-based learning, maybe a little history in the storylines, I think is always a good thing as well. And you know, again, this engineering thing I think is an interesting direction. You know, it needs a little work as far as figuring out, well, where are we going to really start as far as a K-2 learner doing engineering. And again, I kind of mentioned in the last video, you know, I think honestly it's just got more to do with getting their hands on things, playing, you know, building things, you know, more than starting to actually think analytically, but just really starting to maybe strengthen those hand to mind connections is sort of a really important part of the development process at the younger grade. So, all right, everybody, I hope that you found this interesting. We're about out of time here, so I think I will call it quit for lesson 3 of Get in Gear Science Educational Standards. Have an awesome day. I'll see you soon.